Nice. That's correct. So we define a computer as basically something that can compute information. It passes information and computes that information. A computer system. What's a computer system? Yeah, monitors, keyboards, and the actual computer itself, the CPU. I got some examples. So like one example, a laptop here, got the monitor, keyboard, the mouse. Okay, one example of computer system. Another one is this little device that a company has designed. Let me just focus this for a little bit. All right. It's really small, right? This is, right, this little device here is the CPU. It's an little 8-bit processor running at 10 megahertz. Most laptops today are running like dual core 3.3 gigahertz. This is 10 megahertz. This is even older than probably 20, 30 years ago. And then these three things here, these two here are called gyroscopes. They measure angular momentum. And then I have accelerometers. Accelerometer right here. This measures acceleration. And so what my company is trying to do with this is basically it's a computer system. There's no keyboard, no monitor, but it still measures and computes. The little processor measures and computes the acceleration and angular momentum from these sensors on here. So we can see that another computer system without keyboard and mouse. Right? And then we have a microcontroller, another computer system. Zoom it out here for you.
Still a little blurry. There it goes.
Yeah. It's either really slow and really fast. Alrighty. This is from Motorola. This is a microcontroller. Here I have some buttons I can push. Some buttons here I can push. There's some LED lights that can light up. This is the processor here. This is a RS-232 port, so we can communicate out to the world through the RS-232 port, and we have the USB port here, which we can also communicate out. So, and also see there's no keyboard or monitor for this one as well. So there's multiple computer systems. We don't have to have the actual monitor keyboard to actually define it as a computer system. But it has to have basically power. Be the main difference between like an abacus or those kind of things. Those are actually mechanical devices, and a computational computing device is electronically operated by. So. Okay. Let's see if I go here. So how does a computer define this mathematical operation? How does it actually do that? Doing one. Yep. Basically, is you want to define, that's basically what we're going to try to do in this class. Basically is, when you write a C instruction or C# or Java, those kind of programs, high-level programs, we're going to actually see how bits get interpreted into gates that make a processor, that there's instructions that tell the processor what to do, and makes up our C programming and our Java program or C# program. And things like this is like, mathematically this is impossible, right? But in computation it is possible. So we see how we do that in this class. But my computers, only do what we tell them to do, right? Even though we get really mad or frustrated, especially with Windows, it does things that we don't want it to do. But you only do what a programmer tells it to do. And so don't get mad if the program doesn't work, because it's doing what you told it to do. And so we're just going to do understanding what is going on underneath. The main goal of what we're going to try to do this semester. So we have two themes in chapter 1 that we're going to talk about. It's a thing called abstraction and hardware versus software. So we have abstraction. If you read the book, we talked about a taxi driver getting directions to the airport. How many different ways could we give directions, let's say, from BYU to UVSC? Infinite amount of possibilities. Like I said, we can just go down University Parkway and go that way, but we can also say, you know, you go up to Salt Lake, up to Boise, Idaho, over to New York City, down to Florida, back over to Arizona, and back up. There's millions and millions of possibilities. But the key is that we get to a simplified solution, and then we can live with just saying to the taxi driver, to somebody, you know, just head north or go to the airport. But if something goes wrong, if the car breaks down on the way, do we know how to fix it? Or do we need to know how to fix it? Where do we want to live with abstraction? That's why kind of like we break up degrees and the way we break up degrees. Like software engineers, you know, they're really high up, like management like people. And you have like computer scientists, you know, people who do C++, Java, those applications. Then you have like computer engineers who are down in C, doing embedded processor and design. And then you have electrical engineers who are doing the circuitry. So like what level do you want of abstraction do you want to see in your computer curriculum they want? The key to remember though is even no matter what level you're at, if you're high management to being a high-level programmer of C#, you need to know that there is no difference between hardware and software, right? There is no hardware people, there is no software people, right? Because a hardware person needs to know what the software people want to do. They have to know what they want to solve, what problems they want to solve, to know to make the hardware do what they need to do. The software needs to know what the hardware people are doing to, one, know their limitations, know how much memory their device has, how fast is it, can it actually compute what they want to compute, right? So that's why I just try to stay away from, is there a hardware or software people? So today, from now on, we're not either. Okay? Computer scientists are not hardware or software. So keep that in mind. So, anyone disagree with this? Any computer, given enough time and memory, are capable of computing exactly the same thing. No arguments? Yeah.
No, you need certain, like a computer that doesn't have a graphics card, for example, might have enough memory to do some calculations, but might not be able to output it, if that makes sense.
Well, I guess the problem would be is if let's just say they're built, let's just do addition. Let's do like this x plus 5. Let's say both computers can both do that addition. They, even though let's say this computer here and this PDA, like I said in my little processor there is 10 megahertz. This guy is 3.3 gigahertz. He actually only does it faster. He'll do it a lot slower, but they still do it, no matter what. So long as we have enough memory and time, any computer can compute same problem, as long as the hardware is designed to actually do that arithmetic, which most of them can do addition, subtraction, and move data, which that's basically all we need a computer to do is do arithmetic and logic and move data. And so all computers do that. So the said, given time and memory, we can compute anything. Like I said, a computer 40 years ago can't do anything more than a computer today can do. Right? You can just do it faster and more of it. Right? Except some of those guys who are in extreme gaming, your old school computers, they can do it. They'll just be really, really slow, and they'll probably run out of memory. That's usually when your problem runs into. They can actually still do it. It's not playable. They can do it. So we're going to start with the history of computing. Right, it's back, like early man stages. You had Chinese who invented the abacus. We had mechanical devices by the Greeks. They were either devices that required human interaction, crank some lever or flip beads. I'm from a small town in Washington State, and we had an old store, and they had an old register, and you had to pull a crank to do the arithmetic on a mechanical device, and it only did addition. It only did that kind of arithmetic until the turn of the last century. We had people like Alan Turing. Turing machine is not a real machine. It's just an idea that he had from observing people and what they do, how they solve problems, how they compute information. And so he came up with this idea of taking these boxes. We call these boxes black boxes. And even though we might just not define, we don't define what addition is, but it does addition. So this black box takes A and B, adds them together, and outputs the result of A, B. So this is what we call a Turing machine. So it does one thing, it does addition. Another machine, another Turing machine, is multiply. A, B is our inputs into our black box here, and then the output is the result of adding A and B. And then we can do this with these boxes. We can put, if you want to think about it, we have the add and the multiply inside this box. So there's boxes inside this box. So then we can say A, B, C. So A plus B, and the next one's C, which goes to our multiply, that result into our machine. And so a Turing machine can be made up of multiple Turing machines. And so that's what we basically get into our universal Turing machines, which are basically our modern computers today. So we can actually program multiple different boxes to do things for us. So that's what we're doing when you're programming. We're saying add this, we're going to add multiply, and the Turing machine will compute this for us. So here's the example of the Turing machine. If you go online, there's actually, on YouTube, there's a good video of one working. What it is it kind of like you have this tape. So these is kind of like a so it's like a tape that's going through some wheels on the side here, and on this tape we can add. We use that one box that we had, the add. So in the Turing machine, we have letter A, we have B plus B. So the Turing machine, it reads the first letter, A, runs through and finds out, oh, this is my operation, this is what I need to do. So know it now, it needs to know it needs to add. Then it reads over, according to what the add or this operation is, it's gonna look for another operator at the end. It's another B, so then it computes it and then writes our result here, which will make it RIC for the result. So it's gonna write the result on the tape for us. And then it's gonna keep either, according to whatever happens outside, it'll keep rolling through. It might be like a stop command or reverse back and do something else. It'll keep going back and forth until it stops. So basically that's like Turing's idea of a machine that could do computation. And so later they took that as ideas and made what we know of today as modern computers. Technology, gotta love
I'm doing what you're telling me to.
it. Yep. There you go. I don't like this room, if you want to know. Like this room teaching. I don't get a lot of whiteboard space. By next week you'll understand what I'm talking about. I don't know. The whiteboard's in the way. I was writing on it. So now we're going to go talking to solving problems and constraints of solving problems. Forecasting the weather. Why is time a constraint for weather forecasting?
By the time you actually figure out what's going to happen, it's already happened.
So there's no point of telling me what last night's temperature was now, because it was last night. I don't care what happened. I want to know what temperature is right now. It's really important for maybe tornadoes, right? Hurricanes, you know. Back 100 years ago, we didn't have technology, you know, to know those things, to warn people of the weather, you know. Say we had a snowstorm coming today. Would we like to know that yesterday to prepare for it today? Next frame of an animation. Why is timing important on animation in a movie film?
If the clips mixed up, then it's not going to be
Yeah.
logical.
It'll be logical. Or my favorite one is if they're not, you miss them, you skip, or so you have like jittering, like old school movies. You'll see the flickering of the actors moving along. So it messes up the smoothness of the film. Or if you don't get the animation and the voice in sync. I watched a movie this Christmas break where it was an old school movie and the voice was not connected with the actor's voice and it was really annoying to watch. So timing is important in that constraint. Cost. Why is cost a constraint for cell phones?
We make an expensive cell phone.
Yeah, so no one can buy it. Even though I think Apple, those guys are now doing something. People are still willing to buy them for $400, $500. To me, it's a phone. I just need to call somebody. I don't need to text them. I don't need to look at the internet. I'm on the internet all day, so I don't need a phone that does that. I just need to call. So, that's a constraint on the phone. A car. What's the cost constraint in the car?
The cost of leases.
Kind of the same thing as a cell phone. The more bells and whistles you get with a phone, the more bells and whistles you get with a car. Like, I have a new car. It can have a Sirius radio. It has Bluetooth. It has a USB port that you can hook your iPod to. That's happening there. It can diagnose itself, so it will send 2 UV emails saying it needs its oil changed, the tire pressure's low, the transmission fluid needs to be changed, the oil needs to be changed. I mean, how much do you really want to pay for all those things that you can do for yourself? And so, basically, your users, what do your users want in their cell phone? Do they just want to make a phone call, or do they want the internet? Do they want to live stream videos on their cell phone? You know, they're willing to pay for those kind of things. So that's one of the things we look at when we're designing software or hardware. Is what does our user want to have? And then on a electrical or a electrical engineer's side of things, power. Why is power important on a cell phone? Like, what's the constraint on that one? Battery.
Battery only lasts 2 hours.
Yeah. If you have a cell phone that'll last you 2 hours, it's kind of worthless, right? It's not really a portable device. You got to constantly have it hooked up to the wall. And so, like my laptop, I'm actually quite impressed that for 2 years. It still lasts 10 hours. While I don't actually do any intensive things with it, it lasts 10 hours. And so, that's kind of nice. A handheld video game. It's like the old Nintendo Game Boy, or what's the new name, DS or something like that. Why would a user care about power on that one?
You'd be in the middle of something, some important stage in your game, and it dies.
Yeah, user doesn't want to have those kind of things. They want it to last a decent amount of time. Your iPod, like, you want to listen to music all day, not just for half an hour. If I have half an hour, I might as well put the CD into a CD player and listen to that. And so we have all these kind of ideas of constraints into our programs we design. Basically, we look at the problem that we are brought with and find out, we categorize them into our constraints. What's our constraints? What are people going to want to buy? What do we have to have? Like, this is like critical. Like, what do we have to have? What are people willing to pay for? Kind of thing.
Does time also have to do with, like, is that talking about processor speed, things like that? Is that what you're talking about?
It can be. If you, a good example would probably medical devices. Like, if you have a heart monitor and it has really slow compute time, you know, doctor wants it live, and so that way you know what his patient's heart rate is. If you get too slow, he's not getting the information that he needs as soon as he can. Like with my 10 megahertz processor is, I can wait 10 milliseconds for it to compute result, because I don't need it every 1 millisecond. So one of those ones where timing is a processor thing. How, if you have a person who's designing a video game, say, they want it to be as fast as possible for the user to interact with the game. If they have really slow, the user might want to buy the game because it's too buggy, it's too slow. Same with a web browser, or you're watching YouTube videos and you constantly have to buffering and you're waiting for it to play. You ever watch the movie or video that keep stopping and waiting for it to buffer? You don't want to watch it. You stop watching it. so, those are the kind of things in time that you think of. So we kind of have our problems, and then we break them into how do we solve the problem, basically in algorithms. Then we have the language, what language you want to use. Then after we get past this basic line, you want to say is, this is where you've been in 1400 and 1410. You've been up above here. Basically, we've given you the problem, probably given you the algorithm, and we've given you the language, right? Basically, is we're all working on Intel, or IBM, ISA, instruction set architecture, Pentium, AMD processors, and then of course how they build and design that, like of how they do that. Basically, we were always looking up here. We always assumed that we were always working on the same PC processor, but this could change, and so we have options. So that's what we're going to talk about is the options we have. So once we've got the design or our problem, we choose the algorithms, the data structures, basically is how we're going to solve our problem, how we're going to compute the problem. Then we have to define the language, right? This is where we can say, hey, you got C, C++, Java, Python, Ada, Fortran, you know, tons and tons of options that we could use for solving a program. And then those languages get compiled down into instruction set architecture, or an ISA. So that way it's machine instructions, converts it into machine language. All right, so this is basically, this is where we're going to be at. We're programming in C# or C++ or Java here, in your last classes. We're now going to skip the whole compiler part, and we're going to program straight ISA. Basically the lowest a human being can program a computer is what we're going to be doing here. We're going to be, if you want to say, we're going to be the compiler. We're going to take our C and Java code, and we're going to make it write assembly code. Yeah.
Why would you need to program an assembly language rather than like a high-level language?
I program in assembly. If you're a OS designer, OSs, they give us the meaning behind C, C++. They're the ones who interpret what those languages are. So basically, how you can compile down into assembly architectures, you need to have previously defined assembly code that will do this code, right? And then there's sometimes where assembly code is actually faster to do it in assembly than it is in higher level languages. Sometimes there is no higher level language that will actually be for specific architecture, or it's a cost. My company, it costs us $1,000 a year to buy the compiler for my microcontroller, just so I can compile C code. But I can do all my assembly code for free on the device. So it's also a cost issue. Drivers, people who write drivers also write assembly code. It's a lot faster. You can get at, basically as assembly, I can get at everything inside the processor. So hopefully I kind of answers your question. Basically, it's up to the user of why they would want to pick doing it in assembly code or C# or those kind of languages. But the only thing always the meaning is, no matter what, your high-level language is broken down into assembly code. So no matter what, it is assembly code in the end. So somebody has to build the interpreter from the higher level languages into assembly code. So then once we have the assembly code, it's designed for a certain architecture, certain processor. Like we have, you know, your AMD processors, your Sun processors, AMD processors, Motorola chips, tons and tons of options for what process you want to use. And then we're not going to talk too much about this in the class. Circuits and devices basically is how is your circuit laid out, how do they build your circuits. Transistors, electricity, power, those types of things are involved in those kind of circuitry. So we're going to mention them. I'm not going to test you about those that low, but we're going to talk about it. So review again over of those categories again. So the problem statement basically you want to say is your natural language, English, French, Spanish, all those types of languages. And then we have the algorithm, the mathematical interpretation of our natural language. And then we take those and we make a program. Basically, it's our C++ or C#, depending on what we want to solve. And then, no matter what, it's always broken down into an ISA. So each processor has an ISA, so that way we can actually do the computation in the processor. And again, the microarchitecture, your processor, different. Not every ISA works on every processor. If I show those processors again that I had over here, they're Motorola chips. Motorola ISA does not work on an Intel chip. Right? There are different implementations. They have different instructions, like languages, designed to do specific things. Our big desktop computers designed to do general processing, to do all types of things. They're really expensive. Cost what, $1,000 for us. My little processor I have here costs you 3 cents, but it's limited on what it can do. Basically, basic addition, subtraction, and those kind of things. So when you design your problem, it's more of like, what do you need to do? What's the cost? And then you find what kind of processor and an ISA that you need that you can use at a minimum amount of cost to solve your problem. And then, of course, we can't do anything about this because the designers of the architecture build the circuitry for the device. They build the motherboard. They build the hard drive and those things that we can connect to help us solve our problem. So, if you want to look at it in graph, is we want to solve the Gaussian elimination problem to solve a system of equations. If you took an algebra, hopefully you know systems of equations. In this example, they used Gaussian elimination. Then they had the choices of languages they wanted to use. It was C. And of course, they went with the Intel 86 architecture, the standard that we all use. Of course, they picked Pentium. And then down below, Pentium's going to use an adder, right? We'll talk about these later. And then what the transistors are made out of, all right? We'll talk about this as well. So there's a small breakdown of basically what a computer has to do to solve systems equations. You go all the way down to transistor level to do that. So starting next week, we talk about bits and bytes and logic. We're going to talk about how bits, ones and zeros get interpreted into doing things. And then we talk about the instruction set and the processor. How does a processor do addition? How does it do x plus 5? And then we introduce you to the LC3 and the LC3 instruction set, which is a very simplified instruction set. Intel instruction sets like 500 instructions that you can do. The LC3 has 14, so it's really small. Not a lot we can do, but it can be really complicated. And so then we're going to talk about basically subroutines or functions. You want to say this is functions. So that way we can reduce code and modularize our code. And then last of all, how does the processor get information from devices and interpreting by traps and interrupts? How do you interrupt the processor? How does it handle that? And how does it do those kind of things? So that's a breakdown of what we're going to do here. So any questions? Right? No questions? Good. All right. We start the fun things on Monday. Be prepared to relearn how to do algebra or basic mathematics. Assignment 1 is due Monday. We're gonna have a quiz over chapter 1, so I would read it. It's probably gonna be, right now it's 8 questions, so it's 8 fill in the blank questions. So definitions, have the questions. So that's that one. And then to read, start chapter 2, pages 21 to 36. Help you get what?
Quizzes in class?
Yeah, quizzes are in class, yeah. Nope. Good class. The only ones that are the 2 tests